Okay, so today is a short screencast about section 1.4 and the beginning of section 1.5. So our aim today is to talk about how to combine functions and how to alter functions a little bit in certain particular ways. And so the first thing we'll talk about is how to combine two functions via what's called composition. And that you can see is the title of the section, composition of functions. So remember that a function is a rule. It's a rule for converting an input to an output, and you can perform rules in sequence. We do this all the time. When you make a recipe, you're performing a series of rules in sequence. When you write a computer program, you're performing a series of rules in sequence. So if we have two functions, two rules, f and g are sort of our favorite function letters, then the way that what we want to do when we compose them is first we want to apply one rule, then we want to apply the other rule. So the notation we'll use for this combination is this, right? So you read that f of g of x. Now we're used to this f of notation. What's different here is inside f, we have another function instead of a number or a variable. But this isn't that big a deal because we tried to make the point before that the function f is mechanical and it will take whatever input you give it and apply its rule to it. So what this notation says is start with the input x, apply rule g to it to get g of x. That's step one. Once you've done that, apply rule f to the result to get f of g of x. That's step two. So let's look at a number of examples. This is really the only concept in this section, so we can go right to examples. So here are two functions, right? I've got f of x is 2 over x minus 3, and g of x is 6x plus 2. So let's look at an example of a composition of these two functions, something like f of g of 1, right? So here I'm trying to apply the composition f of g to the input 1. And the key to evaluating compositions and untangling them is we start on the inside. So we start with the g of 1, and that's the first thing we do. Well, just g of 1 by itself is no big deal. We've been doing this kind of thing all along. G of x is the function 6x plus 2. So g of 1 is 6 times 1 plus 2, which is 8. And that's where this 8 comes from, this 8 right here, right? So f of g of 1 is f of 8. And now this evaluation, again, is straightforward. We're just plugging an 8 into the f function. So the input slot and the f function is right there in the denominator. So f of 8 is 2 over 8 minus 3, which comes out to 2/5. And so that's how you compute the composition at the input 1. And to compute it at any other input would be a very similar idea. So let's look at a couple more examples. Yes, g of 1 equals 8. We know that. I don't know why that's even there. Oh man, these two are just a repeat of the above. Let's get rid of them. Okay, so let's look at, hopefully this is a new example. Yes, it is. So notice the difference between this and this. And the difference is that the f and the g are in a different order. And this matters, right? When we take the composition f of g, we're applying the g rule first and then the f rule. Here, we're applying the f rule first. It's always the inside function that gets applied first, and then the g rule. This makes a difference. When you make a recipe, if you do the steps in a different order, that's going to affect the results. Putting on your socks and then your shoes is not the same as putting on your shoes and then your socks. So the order of composition definitely makes a difference. To evaluate, we start on the inside. What's f of 1? Well, we just put a 1 into the input slot for f, and we get 2 over 1 minus 3. So that's 2 over negative 2, which is negative 1. So now I'm just evaluating g of negative 1, and that's pretty straightforward, right? I just plug into the g function, the input slot's right there. 6 times negative 1 plus 2 comes out to be negative 4. And notice that we get a different answer, right? F of g of 1 is 2/5, but g of f of 1 is negative 4, not the same thing. You can also evaluate compositions with a variable input, right? So what if we wanted to simplify f of g of x? It's the same idea. Start on the inside. What's g of x? Well, g of x is equal to 6x plus 2. So I just make that replacement, right? I put a 6x plus 2 in for g of x. And now I want to evaluate f of 6x plus 2. And we've done a little bit of this before. Again, f takes its input and it puts it into the input slots, right? So the input slot's right there. So f of 6x plus 2 is 2 over 6x plus 2 minus 3. You can do a little simplifying in the denominator and you get 2 over 6x minus 1. And in this way, if I have two algebraic formulas, I can come up with a single algebraic formula for the composition of the two functions. If we do this in reverse order, we're going to get something different, but it's the same strategy for evaluation, right? So here I'm doing f of g of x, here I'm doing g of f of x. I start on the inside. What's f of x? It's 2 over x minus 3. So the f of x gets replaced there with a 2 over x minus 3. And then I just apply the rule g, right? G of input is 6 times input plus 2. So g of this thing is 6 times that thing plus 2. And again, you can simplify a tiny bit by multiplying the 6 and the 2 to get 12. And I get a formula here for g of f of x. And again, notice these are not the same formula, right? F of g and g of f aren't the same thing. Okay, so let's look at a couple of other examples. Again, there are some exercise solutions here. These exercises come from the notes and exercises document, this one right here. I will open these up in the notes I post, but I'm going to skip over them in the screencast and just look at these other examples. All right, so here I have two functions where I have some numerical information about the functions. I have two input-output tables for the functions, and I want to go ahead and figure out some compositions. So how would I do, let's say, g of f of 10? Again, same philosophy. Start on the inside with f of 10. What's f of 10? Well, you can use the input-output table to evaluate f of 10, and you get from here that f of 10 is equal to 8, and that's where this 8 comes from. And then I just need to do the evaluation g of 8, and now I use the input-output table for g. G of 8 is 18, and that's where this 18 comes from. Notice that with tables like this, I'm not going to be able to evaluate any composition that you make up. It has to be sort of structured so that I have the information I need in the input-output tables. Let's look at another example or two. So f of g of 6, I start on the inside to compute g of 6, and g of 6 is right there, right? I find the input 6 in g's input-output table, and the output's 22. That's where that 22 comes from. And then f of 22, so I use the input-output table for f. F of 22 is -3, and that's where the -3 comes from. Okay, one more. So this one looks a little different here, and you can see right at the beginning that the difference is I don't have an f of g or a g of f, but I have a g of g. You can compose a function with itself, so there's nothing sort of off about this. What this means is apply rule g and then apply rule g again. It's sometimes called iterating a function. In any event, as before, we start on the inside. What's g of 13? I find the input 13 in g's input-output table, and the output is 4. And that's where this 4 comes from, right? I replace the g of 13 by 4. And then I compute g of 4. And again, I'm using g's input-output table, right? The output for the input 4 is 19. So g of 4 is equal to 19, right? So I can compose a function with itself. I can compose in either order. Okay, so we've talked about computing compositions from algebraic formulas and from numerical tables. What about from graphs? So here are two function graphs. The blue graph is f, the orange graph is g. You'll notice that they both pass a vertical line test. So these are graphs of functions. So let's see how to evaluate some compositions here. Take, for example, f of g of 3. I start on the inside with g of 3. So now to find the output under g at the input 3, I go to the 3 on the horizontal, right? The inputs are on the horizontal axis, the outputs are on the vertical axis. So I go to 3 on the horizontal axis, and I go up to the orange curve, which is g. Now, in this case, it doesn't matter because it looks like the two curves are at the exact same height at the input 3. And the output value for g looks like it's 2, right? That's the value on the vertical axis. And that's where this 2 comes from. Okay, so that's g of 3. And now I do the outside rule. f of 2, right? To evaluate that, I find 2 on the input axis. So that's right there where the arrow is. And now I'm going to go up to the blue curve, which is right here, and determine the output value there, which looks like it's about 3, right? The outputs are on the vertical axis. And that's where I get the results there of 3. A couple more along the same lines. How about g of f of 5? Start on the inside with f of 5. So I find the input 5 is over here on the horizontal. And I'm going to go up to I'm evaluating f of 5. So I go to the blue curve, which is that point right there. That looks like it's the output value 2. That's where the 2 comes from. And then I do g of 2. So I go to the input value 2, which is right here, and go up to the orange curve, which is here. And that's a height of 5. And that's where the 5 comes from. And finally, again, I can compose a function with itself. Let's try f of 1. So start on the inside with f of 1, right? So I go to the input 1, that's right here. I go up to the blue curve that has height 2. Again, it looks like the two curves are at the same height at x equals 1. But in any event, so that's where this 2 comes from, right? F of 1 is equal to 2. And then I finish by doing f of 2, right? So I go to the input 2, go up to the blue curve. The height there is 3, and that's where the result there comes from. Okay, one final example, and that's probably enough for compositions, and we can move on and talk. We won't do all of transformations in this video, but we'll talk about a good chunk of it. So here are two functions that are just kind of described in words, right? So I have a function a of d. So d is the input to this function. And what does d measure? D measures the number of milligrams of a painkiller that are in a patient's system. Highlight all of that. There we go. And what does that's the input to the function. The output to the function is pain level, right? So usually pain level is measured by giving a patient, asking them to rank their pain on a scale of 1 to 10 or something like that. And then I have this other function m of t. So here, notice the input variable is t. What does t measure? T measures the number of minutes since the painkiller has been administered, right? So notice the different variables measure different things. D measures how many milligrams of the painkiller. T measures how long it has been since the painkiller was administered. And the output of this function is the number of milligrams in the system, right? So the number of milligrams is a function of the number of the time since the painkiller has been administered. So let's try to interpret some compositions. If I look at this composition, so this is a of m of 5, right? Start on the inside. What is m of 5? M of 5 is the number of milligrams of the painkiller in the patient's system 5 minutes after the painkiller is administered. Okay, if I take that number of milligrams, so that is my d value, right? That's worth saying here. Is the d value. And I plug it into the function a, what do I get? I get the pain level. So this whole composition will give me the pain level 5 minutes after the painkiller is administered, right? So it's a way of going from time all the way to pain level, right? I have sort of 3 variables here: time, milligrams, and pain level. And the other composition, if I do this in reverse order, it's worth noting that it doesn't really make any sense, right? If I try to do m of a of 5, the problem with this is that if I start on the inside, a of 5 is a pain level, but the function m doesn't want a pain level input, it wants a time input. So this doesn't really make any sense, right? I'm taking a pain level and plugging it into a function that wants a time input. So sometimes this happens, that compositions only make sense in one direction, especially in these conceptual cases. Okay, so composition is a way of combining two functions. Transformations are ways of sort of changing a particular function in kind of a structured way. So the first kind of transformation we'll talk about is a shift. There are shifts, reflections, and stretches. I think we'll talk about the first 2 of those in this video. So if I take a function f of x and I add a number to it, the effect of that is to shift the graph vertically. And here's an example. So what we're looking at here, this purple curve is the function y equals x squared. This is one of the toolkit functions that was that's in the book at the end of the very first section of the chapter. And so you should be sort of familiar with this graph as one of the basic graphs. If I modify this function by adding a number, right? So notice now the blue curve is the old x squared curve, and the purple curve, I've added 3 to the function. The effect of this is to add the 3 to the output, right? X squared is the output of the function. And this means that all of the heights move up by 3, right? So at any input value, the blue height, the height on the blue curve is the original function. If I add 3, then I go up 3 more units. And since I do this everywhere, all along the input axis, the effect on the graph is to take the blue curve and just kind of shift it up by 3 units, right? So if I keep increasing that shift, you can see that purple curve keeps going up, right? And then as I decrease the shift, it goes down. I can also add a negative number. So that will look like subtraction, right? So say I do x squared minus 3. Minus 3, of course, is the same as plus negative 3. So this is in the same category. What happens now is I'm subtracting 3 from all of the outputs. So if I pick any point along the blue curve, like this one over here, the way I get to the purple curve is by taking 3 away from the output, which means I go down by 3 units. And the effect again is that the entire graph gets shifted vertically down, in this case, by 3 units. And if I keep subtracting more, you can see the purple curve keeps going down further, right? Subtracting less, it keeps going up and so forth. Okay, so that's how you get a vertical shift of a function, is just by kind of adding a constant, and that could look like subtraction. That's still adding just a negative. So those are vertical shifts. The other way we can shift a graph is horizontally. So a vertical shift is up, down. A horizontal shift is left, right. And the way we execute a horizontal shift is not by adding a number outside the function like we do here, but rather by adding a number inside the function. So we add the number to the input, not to the output of the function. So when we do this, let's take a look at a vertical shift here, right? So here the blue curve is the same y equals x squared we were looking at before. And in the purple curve, what I've done is I've added 2 to the input, right? Not to the output, but to the input. And now I have the function, the quantity x plus 2 squared, right? So what happens here is if I take the input, let's say x equals 2, and I plug it into the purple curve, I'm going to get the same output as on the blue curve when the input was 4, because I'm adding 2 to the input. So the way to get the output value at this point is to sort of go over to x equals 4 and kind of grab this blue output and pull it over to the left. And I do this at every single point along the input axis, which has the effect of taking the blue curve and pulling it to the left by 2 units. Now, what is unintuitive about this is we're adding 2 to the input, but the result is to shift the graph left, not right. Left feels like a negative direction. So this is a little bit counterintuitive. Be careful of this kind of example. And if I increase the shift, you can see it just shifts further to the left, right? And then less far to the left. Just as before, I can add a negative number, right? So -1 is the same as plus -1. And the effect of that is just to shift in the other direction. You can see now that the purple curve is to the right of the blue curve. And if I increase that, there we go. And if I increase that number, you can see the purple curve shifting further and further to the right. So again, on horizontal shifts, be careful. When you subtract from the input, that shifts to the right. When you add to the input, that shifts to the left. Okay, let's look at a couple of exercises here. These exercises come from the notes and exercises document that's posted on Canvas. So this is the first one that I'm going to look at, right? So I have this graph of a function here in blue, and I just wanted to sort of sketch a picture of what these various transformations look like. Now, looking at these, hopefully we recognize that the first 2 are vertical shifts, right? Here in the first one, I'm adding 5 outside the function. Here I'm adding -10 or subtracting 10 outside the function. Since I'm adding to the output or outside the function, the shift is going to be vertical. The second two, on the other hand, I'm adding to the input of the function, so those are going to be horizontal shifts. This shift here, the very first one, is going to be a shift up 5, right? It's a vertical shift, and because I'm adding 5, the curve's going to go up 5, and this shift is down 10. So what that looks like, and it might take a little time to sketch the graph here, here's the up 5 shift, right? So the blue curve is the original, the one that you were looking at a minute ago in the exercise. And the orange curve is what happens if I shifted up 5. I just move the curve up 5 units. Similarly here, the blue curve again is the original, and the orange curve is just a shift down 10 units. And you can see, like if you check over here on the flat part, the orange curve looks like it's at about 45, the blue curve at 55. So that's about right? That's a downshift of 10. This here, when I subtract 4, here, this is the counterintuitive one. That's a shift to the right by 4 units, not to the left. And this shift is going to be to the left by 3 units. Okay, so in pictures, the blue curve, so they go over the top of each other a little bit here. The blue curve is the original, and then the orange curve shifts right by 4 units. So a good place to look is like at this corner point right here. You can see on the blue curve, that corner is at x equals 5, and on the orange curve, it's moved over to x equals 9, 4 units to the right. Okay, and the final one, whoops, what did we say? This was a shift to the left by 3 units. And here's what that looks like, right? F is the blue, and you can see, again, look at the corner point here. The orange curve is 3 units to the left of the blue curve. All right, let's look at one more example from the notes and exercises and then talk about reflections, and that will be good for today. What if we start, so let's go to the exercise itself. What if we start with an algebraic formula instead of a graph? Now, how do I make a function that shifts this function in some specified way? So let's say I want to shift it to the left by 6 units. Well, I know that to shift to the left by 6 units, what I want to do is I want to add 6 to the input. That is, I want to compute, whoops, here we are. I want to compute f of x plus 6, right? So that first thing that's highlighted in blue, that's the first thing I want to write down, because that's how I'm going to execute the desired shift. And from here, it's just sort of old function evaluation, right? This function has its input slot here and here. It takes its input and squares it and adds 3 times input. And if the input is x plus 6, then I should square x plus 6 and add 3 times x plus 6. Now, to be sure, you could FOIL this out and combine like terms and simplify, but that's all algebra. So I think we've done the hard part here. Okay, that's to the left 6 units. What was the next one? Down 7. So to shift down 7, I want to subtract 7 outside the function. So from the output, not from the input. So what does that look like? That's just going to look like f of x minus 7, right? Notice the difference how the minus 7 is outside the parentheses, whereas up here the plus 6 is inside the parentheses. And this one is a little easier to execute. F of x is just x squared plus 3x. So f of x minus 7 is just x squared plus 3x and then minus 7. And that's that. That's the desired shift. Notice that we can execute multiple shifts, right? So we could, for example, shift up and to the right, or down and to the left, or some other combination of those two, right? So if I want to go up and to the right, I have to do these sort of one at a time. Going up 1, I'm going to add 1 outside the function, and to the right 5, I'm going to subtract 5 from the input of the function. So what does that look like? Right? Well, this part right here, that's a shift to the right by 5 units. Is that what I want? Yes, right by 5 units. And then when I add 1 outside the function, that goes up by 1 unit. So here is how we do 2 shifts at the same time, right? And it doesn't, in this case, matter what order you do the shifts in, right? If you go up and then left or left and then up, you're going to wind up in the same place. And from here, it's just function evaluation, right? As above, the input slot for f is right there. So f of x minus 5 is x minus 5 squared plus 3 times x minus 5. And I just have this plus 1 on the outside. And I did a little bit of simplification. You could do some more there as well. But again, once we get to this point, it's all algebra. Okay, last one. Let's go down 2 and to the left 3, right? So to the left 3 means I'm going to add 3 to the input, and down 2 means I'm going to subtract 2 from the output. And what that looks like is this, right? So I'm going to add 3 to the input there, and then subtract 2 to go down. And from here, it is similar, right? So here's f of x plus 3, right? The quantity x plus 3 squared plus 3 times x plus 3, and then minus 2. And again, you could do some foiling in algebra here to simplify this, but it's all algebra from here on out. Okay, we're getting a little long today. Let me take a quick look ahead. Reflections and stretches. I think I'm going to save reflections and stretches for tomorrow's video. So we'll stop here having done compositions and shifts. And in tomorrow's video, I will start with reflections and talk about stretches as well, and then talk about inverse functions in the final section of the chapter. Okay, take care, everybody.